Hello, welcome to this video. Today we're going to look at this formula and we're going to derive it. So we have n factorial is the product over all p prime numbers of p to the power of the sum as k goes from 1 to infinity of the floor of n divided by p to the k. This seems way too complicated to be useful, but the way this does help us, in a way, is with mathematical Olympiads when looking at, say, factors of factorial numbers. How many of them, for example, are divisible by 5, 3, and not 7, for example? Or how many are not squares and are cubes, or something like that. And for that, you'll have to use the prime factorization of factorial numbers, and this formula will be able to help you. And I'll explain how you use it because this seems very scary. So let's begin. First of all, we have to establish another formula that will help us, which is how many multiples of m are there that are smaller than or equal to n. So what I mean by that is, let's ignore this formula for a second. If we have, for example, say n is equal to 13 and m is equal to 3, then we'll have a formula that will be able to quickly tell us that the answer here is 4. Why is the answer here 4? Well, because if we look at the multiples of m, the natural multiples, we have 3, then 6, then 9, then 12, 15, and so on. And we want to find how many are there that are smaller than or equal to 13. Well, that's obviously these 4, and the rest here don't count. They're obviously bigger than 13. So the answer for this example is 4. And we want to find a formula for all n and m, like this. So let's quickly do it, because again, that will be very useful for finding this. So now, let's see. So, let me remove this example because it's so confusing. It's confusing. So, let's set the number equal to k. The amount of multiples that are smaller than or equal to n, the multiple of n. Well, in other words, we can look at the multiples and say, this is m, then 2m, then 3m, and so on until what? Well, because the amount of multiples is k that are smaller than or equal to n, that means that the last one will be m times k. So we have actually k multiples of it, and only those are smaller than or equal to n, meaning that the rest of the multiples, so n times k plus 1 and onwards, are bigger than n. So what this tells us is the biggest multiple here, which is m times k, is smaller than or equal to n, but because it's the biggest one, that means that the next one, which is n times k plus 1, must be bigger than n, because otherwise it would be part of this group, but it isn't. So now we have this equation, and we want to find k. It seems a little impossible because we want k is equal to something, and here we only have smaller than or equal to, but here's how we do it. So first of all, we're going to divide by m to get rid of this n, to get rid of these m's in the front. So we get k is smaller than or equal to n divided by m, which is smaller than k plus 1. Now we can use the floor function. The floor function goes something like this. Not something like this, exactly like this. The floor of any number is the biggest integer smaller than that number. So smaller than or equal to that number. So for example, the floor of 3.5 is 3. The floor of negative a half is negative 1. The floor of the square root of 2 is 1. The floor of a whole number, say, for example, 4, is that number 4. Because we're looking at the biggest integer smaller than or equal to this. The biggest integer smaller than or equal to this, and in this case it's obviously 4, when this number is an integer. And that means that by this definition we can say that if we have x as the as the floor of y, that means that x is smaller than or equal to y, and y is smaller than x plus 1. That is, you can say, the definition of the floor function. And that is exactly what we have here. So this tells us that k is the floor of n divided by m, which is what we wanted to get. We want to get a formula for k, which is the amount of multiples of m smaller than or equal to n. And obviously m and n are positive integers. Now let's use this over and over again for this formula. So let's erase the board and do that. Okay, now let's actually prove this formula. So the way we're going to derive it is, this is simply the prime factorization of a factorial, because it's the product over all primes of a prime to the power of something. So what we're going to do is simply look at a certain prime number to show why the power works, and then we're going to see quickly why that works for all prime numbers. And that will mean that the prime factorization of it will just be the product of all the primes to the power of this, which is the power of each prime. So let's begin. So let me pick a simple, easy prime. How about the smallest one? 2. So what we want to do is, let's look, for example, at 12 factorial and see how we find its prime factorization. So 12 factorial is 1 times 2 times 3 times 4. Okay, so this is the definition of the factorial, multiplying each positive integer from 1 till that number. So this is 12 factorial, and we want to find the power of 2 in its prime factorization. So first of all, obviously, every second number is even. So, which means that we need to account for every second number, account for 1 power of 2. So we need to get the amount of 2's as the amount of numbers divisible by 2 smaller than or equal to 12. So that means we need to account for all of these, which by our formula we can simply say the floor of 12 divided by 2, which is 6. That means that we're accounting here for 6 2's. But what about the ones that are divisible by 2 squared, aka 4? Because those we counted in evens, on the evens, look 4, 8, and 12. But we didn't count them as powers of 4, we counted them as 2. So they are 2 powers of 2, and we only counted them as 1. So for each for each multiple of 4, we need to account for another power of 2. But hold on another second, because what about the ones divisible by 8? Because so we accounted for these twice. What about 8? It needs to be accounted for 3 times, because this is 3 powers of 2. So for all the powers of 8, we need to account a third time. And here it stops. And here, this is where it stops, because the next power of 2, which is 16, is bigger than 12. But you can imagine that this just continues on forever for all numbers n. So what did we do here? So the power of 2 is this. First of all, we looked at all even numbers and accounted for each one as 1 power of 2. That's the amount of numbers divisible by 2, smaller than or equal to 12, which is the floor of 12 divided by 2. And the next one is the floor. The next one is the floor of 12 divided by 4, because we need to account it again 1 time for each multiple of 4. And the amount of multiples of 4 is, by what we derived earlier, the floor of 12 divided by 4. And now we need to account again for 8. Because for 8, 8 needs to be accounted for 3 times. So this needs to be accounted for another time. And that's for all multiples of 8, which there are the floor of 12 divided by 8 of them. And this continues on forever. Why does it continue on forever? So the floor of 12 divided by 16, plus the floor of 12 divided by 32, and so on, for all powers of 2. Why? Because we're just adding on zeros. 12 divided by 16, 12 divided by 32, and so on. They are between 0 and 1, so the floor is 0. So we're basically adding on nothing. This is the power, we're just adding on zeros. And it's just simple to that as infinity. If you use it for a specific case, you just stop at the biggest power of that prime, smaller than or equal to your number. But in the actual formula, I'll just write it as a sum to infinity, because it doesn't matter. The rest are zeros. And you can obviously see that if we instead look at the number 3, the power of 3 here will be, well, first we have to account for all multiples of 3 1 time. So that's 3, so instead of above, so that's 3, 6, 9, and 12. So that's how many numbers there are divisible by 3 and smaller than or equal to 12. So that is the floor of 12 divided by 3. And then we need to still look at what about the 9, because there is still another 9, which should be accounted for as 2 3's, but we only looked at it as 1. Meaning that we need to account for, again, all multiples of 9, and there are the floor of 12 divided by 9 of them. And again, this continues on forever, because the rest are zeros, because the next power of 3 is 27, which is obviously bigger than 12. And this obviously works for all primes, meaning that the power of each of each prime for n factorial is the floor of n divided by p plus the floor of n divided by p squared plus the floor of n divided by p cubed, and so on forever. And another case is, what about when the prime is already bigger than the number? What about 13? Because 13 or a multiple of 13 cannot appear in 12 factorial. So how can this product go on for all primes? Well, that's simple. Because there aren't any multiples of 13, each one of these floors of 12 divided by a power of 13 would be already 0, each one of these floors. Because obviously 12 is smaller than any power of 13, any natural power of 13. So, and 13 and all other primes beyond, we have that they're just, that their floor is just 0, so the power is 0, so they're not accounted for in the prime factorization, which is what we want and know should happen. So generally, this is the power for each number, prime number p, which we can write like this. Sum as k goes from 1 to infinity of the floor of n divided by p to the k. For each prime number, this is the power, meaning that this, we need to take the product of this, erase this here, meaning that we need to take the product of this for all primes. And this is the prime factorization for n factorial. And also I should say that this is not a rigorous proof. As you saw, I looked at it intuitively. How many? I looked at it intuitively. How many are there that are divisible by 2, then 4, then 8, for 2, and for 3 is 3 and 9, and so on and so forth. But it is still quite cool to me that even with intuitiveness, you can still get this formula. It looks very scary and not intuitive. But finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading you more interesting problems and things like this in the future. Finally, that's it.